Can you check on your phone if it's...
Yeah, of course. I didn't see. Oh, is it? Oh, I said. Okay, question.
Let's check audio.
Wait, where do I check it? Do I like
This goes YouTube. Oi, oi. I think we just have to not touch this laptop.
Okay. You guys want to try speaking?
Testing. Oi, oi. Testing.
Yeah. Why is this like the most like? It's hard. Bro, freaking China. Like, is the audio coming from the topic? Oh yeah, it's coming from the video. Okay. Like ours. Yeah. Oh. Okay. What's that?
Testing.
Oh wait, no, it's lagging though. It's lagging.
You want to charge on here? There's a charge on here. Yeah. Wait, this.
Yeah. With this one.
You want to charge on here? There's a charge on here.
Why did you use that?
But it's like competition.
You're actually for real, Jen.
Yeah, there should be a side. Nice JS.
I'm older than you. Yeah, you're actually for real.
Really?
Like, actually,
Huh? Wait, it was actually ours. We don't talk about it. It was like, we were like right 6, and then the studio was really good. I got the love.
I don't like you, but I think
we just kept on starting. We lost so much money around.
Alright, testing. Another test from far away. That's fine.
it's fine. Yeah, but it was.
Does it like sound bad? Alright, testing.
It comes like 30 seconds. Yeah, but it's
That's fine. Another test from far away. Hello, team.
Bro, I was like, half my team just like, also you can hit we somehow ended up.
Wait, is this on?
So it's
Shit. All I can do is just like, that's what I'm saying. Oh wait, no, it was you. No, that's actually racist. Wait, I like how
Pretty like, we didn't mom it. This is a little Also, he said like the sound works fine. Like he could hear just gospel. He's like Wakil hears just gospel.
Feedback's
Yeah, what do you think it's like? Like,
just coming from like the should be fine.
He's like the sound works. Like he could hear just he's like walking is just
So we're just talking to the mic.
Should be fine.
What the actual?
this is should be fine. You can clip onto your shirt.
Yeah.
I really top one out. I'm like,
So we're just talking to the mic. Oh, it's like what the actual? If you squid, it's not too bad.
Hey guys. Can you guys hear me all right? Testing. Hello? Yes. Thank you so much for coming. We're going to get started now. Hey guys. Can you guys hear me all right? Testing. Hello? Thank you so much for coming. So thank you guys so much for coming today. We are SQT, Sydney Quant Traders, and we're joined by the very lovely SUMS as well, the Sydney Union Maths Society. Today we're going to be going over some foundations of maths and combinatorics, and essentially this is the backbone of what a trading interview will look like at a lot of quant firms these days, and so that's what we're trying to help prep you and share some knowledge from our very knowledgeable education teams. Before we get started, if you guys haven't already, please sign up. Takes about 30 seconds just for some details. And essentially this is the backbone of what. Cool. Well, I'm going to pass it over to Eamon, who's going to get started. So thank you so much, guys.
So yeah, thanks for coming today. I'm assuming most of you guys are here because you're like somewhat interested in quants. So before we start, like I will tell you guys, the content in this workshop isn't like extremely complicated. As a matter of fact, a lot of it is actually quite simple and perhaps something you've even seen in high school, right? But the point of this workshop is that you have a very first principles and foundational understanding of combinatorics. So like in quant interviews, the questions they ask often aren't that necessarily complex, but they require you to like understand how to break down a problem into like its really basic form, and that's really, really important. So yeah, and before we even start the talk, we might as well introduce ourselves. So go first, Jed.
Yeah, so I'm Jed. I'm a third year here studying math and computer science, and I'm an incoming graduate trader at October.
Yep, so I'm Aditya, and I'm a fourth year at UNS doing computer science and maths, and I'm part of the education subcommittee here.
My name's Eamon. I'm a first year at UNSW studying math and CS, and I like math Olympiad, so that's a bit of my background. So we're going to get started with the talk.
So I'm Aditya, and
so this talk is called How to Count, and combinatorics provides basically, right? So wait, is that the only way we can move forward? Okay. So how to count. So here's a very introductory problem for all of us, which you've probably seen in like year 3. How many outfits can be made from 4 shirts and 3 hats? Does anyone want to volunteer to explain this problem? Yes, sir. Is that the only way we can move forward? Do you want to explain how you got to 12? Okay. Does someone want to explain how we got to 12? Well, that is a great explanation, but why is it 3 multiplied by 4? Yes, sir. Do you want to explain how you got to 12? That's a not terrible explanation. I like that. Okay, so what's next? Okay, went backwards. Next slide is what is a configuration? Well, as we see on the slides, a configuration is a way or a sequence of decisions that constructs an object, right? So each leaf node in this Each leaf node in this decision tree corresponds to a different configuration, right? That makes sense, you know. So we got, 4 times 3 in this case. That's pretty simple. Okay, what's next? The first thing we're going through is the addition principle. And addition, I hope all of you can perform. It's probably the first thing you've ever learned in mathematics. So if 2 tasks are mutually exclusive, does anyone want to explain what mutually exclusive means on a very first principles level? That's pretty simple. Okay, what's next? The first thing we're going through is the addition principle. And addition... Yeah, so I like the explanation, right? So basically, what you're trying to say is that if you have a Venn diagram, like the mutually exclusive events are like the ones with like no intersection. Like they just can't happen at the same time. They can't like, yeah, that's not possible, right? Like if you have a single card, it can't be both a heart and a jack, right? Those are mutually exclusive. And if task A can be done in M ways and task B can be done in N ways, there are M plus N ways to do either A or B. Now that's pretty simple. So here I have an example or something to prove for us, right? It's proved N choose K is equal to N minus 1 choose K minus 1 plus N minus 1 choose K. And perhaps I've jumped forward a little bit because we haven't even touched terms and commas yet, but this basically means choosing K objects from N objects. And yeah, you guys get it. So would anyone have a guess about how we can approach this problem here and why is it logically true? Yes, sir. It is indeed a combinatorial argument here, but what combinatorial argument are we exactly applying to get this identity? Yes, sir. Pardon? A committee? May I ask what a committee is? Yes, sir. It is indeed a combinatorial argument here, but I got lucky, that's what you're trying to say. Does anyone want to perhaps explain how we can apply the addition principle to get this identity? A committee? May I ask what a committee I mean, I can give you guys like a minute to think about it. I got lucky, that's what you're trying to say. Does anyone want to perhaps explain how we can apply the maybe 10 more seconds to get this identity? I mean, I can give you guys like a minute to think about it. Perplexing indeed, right? Well, perhaps the next slide will divulge some information on perhaps this riddle can be resolved. So we can fix one person from the group event, right? Some person, I don't know, Bob. Okay, so every group that we choose of K people either has Bob in the group or doesn't have Bob in the group. That is very, intuitively logical, right? You can't have half of Bob in the group. You either have him or you don't. So if you include, where's my? We can fix one person from the group event, right? Okay. Some person, I don't know. Okay, sorry. So if you have Bob in the group, then we have to choose the remaining K minus 1 people from the remaining N minus 1 people, right? Because after we've chosen Bob, the N minus 1 people left in the group, and there are K minus 1 people left in the subset we're choosing. And in this case, you don't even have to understand what choose means. You're on a very, very basic and foundational conceptual level, it makes sense that you're including Bob in the group. And if you exclude Bob in the group, you're still choosing K people in that subset of people, right? But this time you're choosing it from, again, the N minus 1 people who are left in the group after you've removed Bob. So there's N minus 1 choose K ways. And like this, sorry, you have a question, sir? It makes sense that you're including Bob in the group. And if you exclude Bob in the group, you're still choosing K people in that subset of people, right? Sorry, I don't quite understand what you mean. Again, the N minus 1 people who are left in the group after you've removed Bob. N minus 1 choose K ways. And like this, sorry, what do you mean, chuck it in the formula? I mean, yeah, you can always apply the formula to this, right? The formula's pretty simple and it's chill. But this is kind of a cool identity that you can know. It's not particularly is this insightful in any way? Not necessarily. And you're right, this is not going to help us calculate anything any faster. But it's kind of just a problem to show that example of an addition principle, because the fundamental here thing was that one person, Bob, they're either in the group or they're not. So that's a mutually exclusive event. You can't have Bob both in and out of the group. Does that make sense? That's cool. The next very simple concept is called the multiplication principle. So, two tasks in the independence, then task A can be done in m ways, while task B can be done in n ways. Then there are m times n ways to do both A and B. So, I have an example for us. How many subsets does an n-element set have? So, does anyone have any questions about what a subset or n-element set means, or any questions about this problem in general? I'll let it simmer for like a minute or two again. Addy has just asked what a subset is.
A subset is a set where every element of a subset is in the original set. In other words, it's a collection made from the original set. Now, if you have the answer, you can like raise your hand or something. Or if you have like any idea how to approach the problem. N squared. I'd say that's not a bad guess. Do you want to explain why you got n squared? What do you mean 3 times 2n? Okay, so okay, interesting. I'm having to think about what you say. So if it was n squared and you had if you had 3 elements, so it's okay. I mean, you could try count, right? You have consider the set of 1 element, 2 elements, 3 elements, 4 elements. I'm sure you get 6. I mean, we could let you count like the empty set first of all. You could have the 1 plus 2 plus 3. That's 4 so far. You could have 1, 2, 1, 3, or 2, 3. That's another 3. You also have 1, 2, 3. So a total of 4 plus 4, 8 in total for the set of 3 elements. So, yeah. Any other ideas? Yes. Yeah, n squared was very good because you had the right numbers, but they're in the wrong order. So the correct answer is indeed 2 to the power of n. You want to explain how you got 2 to the power of n?
And then for each of them, it's and then it's the same as the so
okay, so that was a fruitful method of proving this using the. Thank you. Hello? Okay, this doesn't. I can let you shout. So so yeah, that is a valid way of doing it. You can create a binomial using like the sum of a bunch of like combinations. But that is not a proof to power of n. That seems so simple. Surely there's a more simple way to elucidate this fact. Yes? That is a very, very good way of approaching it. Any element in the set can either be in the set or not in the set, right? It can't like be halfway in the set, you know what I'm saying, right? So it's either in or out of the set. And you can, for every single element, you have 2 choices. And based on whether you choose whether that element is in or out of the set, your final result will be a unique subset. Right? So, cool. Like we said here, every element you can independently decide whether it's included or excluded. Right? So each element contributes 2 independent choices, and thus, by the multiplication principle, you have 2 times 2 and so on. 2 to the n. Okay. And like I said before, the empty set is counted. I probably should have said that because like it might have been deceiving. It's easy to forget. But by the definition of the subset, like a subset's a set where like every element in the set is in the original set. If there's nothing in the set, then yes. So okay, next slide. Exponentiation. Oh, the number of ways to form a sequence of k choices from a set of n options, the repetition allowed is n to the k. So like again, I think this idea is most clearly shown in an example. So how many functions are there from a k element set to an n element set? You can use the Wakil. Okay. And I'll give you guys a minute to think about this problem. And this time I won't make any comments about your response. I'll just let it simmer and we'll discover it together on the next slide. And feel free to discuss among yourselves as these boys are doing well. I reckon 20 more seconds. Like time's up. Does anyone have any ideas of how we can approach this problem? If not, it's okay as well. We all learn together. Okay, we shall move to the next slide. So for each of the k elements in the domain, we independently choose one of the n outputs. That is like, this like seems so simple now, right? Does anyone know the definition of a function? Like, what is a function? Perhaps, right? Like, one can say a function is a formula, a formula can be used to encapsulate a function, perhaps nothing real to real, integers to fractals, whatever, right? But more generally, a function just takes some sets. I mean, normally you guys might be used to having a set of all real numbers, but it could be literally any sets. It's a set onto another set, right? So the domain and the range. And does anyone know how to tell if a function is not a function? You guys in high school, surely you know this. What is it?
It's going to be 1 to 1, or it's going to be is it? Oh yeah, you draw a line.
So yeah. You can in a function, like you can do the vertical line test if you did high school math, and it's like you kind of have two outputs for the same like input, right? So basically, for each of these k choices, we choose one unique output. But it could be any output. We can repeat the output, but as long as every single input has a specific output. So for every single output, we can choose one of the n options, and then we have n and then k times, and that's the number of ways to form a function, right? So these problems are all very, very conceptual. They're not like, they're kind of trying to think about it, the math is multiplication. Hopefully we can all do it, right? So for quite a bit of like pondering about how this sort of stuff fundamentally works. In this case, it's like, what is a function? Okay? Another example. How many binary strings of length n contain no two consecutive ones? So just letting us know, a binary string is a sequence of integers made from zeros and ones. Computer binary. So you guys know how to think about this as well. I luckily don't remember putting this from here, by the way, so I guess we'll find stuff. Yep. Yeah. Yes. Pardon? I would say the nth number of a sorry sequence, but what was it? I don't quite understand what you're saying. Okay, we'll go with maybe what you're saying, alright. So I didn't quite understand what you were saying, but go to our solution. So oh, so you were saying Fibonacci sequence. Sorry. Okay, I just realized that I can't. What's up? Yeah, lucky is. I don't even know why this is here. That's why I don't remember putting it, but it's okay, you know. So the number of let an be the number of values to the some length n. Yeah, this is really weird by here. So I was a bit confused as well. But anyways, condition on the first bit. So if it's 0, the remaining n minus 1 can be any valid a n minus 1 way. Then the first bit is 1. The second bit must be 0 because we can't have 2 ones in a row. And then it's any valid string of length, you know, n minus 2. Okay, so we just sum and we have the Fibonacci sequence. So the idea here was that like this actually wasn't exponentiation. I think that's how I put it. Like see if anyone's trying to use exponentials. It doesn't work. Kind of evil here. But anyways, yeah, it counts unrestricted sequences. Constraints kind of supposed to do more like careful things. I know, good one getting that by the way. That's pretty tough. Okay. Perms and comms. So solid ice. HC stuff. So permutation, which is very, very important, is an ordered selection. Ordered. Where's my pointer? Here we go. An ordered selection of k items, right? So this idea of order is very important because it makes it what's different from combination. So it's an ordered selection of k items from n distinct items with no repetition. And this will make sense if you think about it a little bit, and we have this formula. But without getting over the formula, let's go through an example, right? So how many ways can a gold, silver, and bronze medal be awarded to 3 of the 8 athletes? Mike? Where is it? Sorry. This one? Oh, this mic, got that. Okay, that's it. How did he get 256? Okay, 888. Interesting. Interesting indeed. I want to comment on that. Yes, sir. How do you get 56? Okay. Yes, you can solve this permutation with 8 that makes sense. But the sum of one will explain why it's not 8 to the power of 3 instead 8 times 7 times 6. Yes. Yeah, you're saying Bolt can't win the first, second, and third, right? Like someone else did the first, second. So there's no repetition. You can't repeat the same person twice. So that's very important. No repetition, order selection. Okay, so that's what we have here. The 8-3, very good. Okay, next slide. That's a pretty easy example. Combinations is an unordered selection of k items from n distinct items. It's kind of an important thing to get ahead around because like half the quant question will require you to calculate a combination of some sort. So this time it's another very simple example of how many ways can 3 athletes be chosen from 8 for a relay team. So does anyone want to first say, how is this different from a, sorry? A relay team is like, don't worry about it, it's the team. It's exactly what we're doing. So we choose 3 athletes, so. Yeah, so exactly how we would approach this problem. So for those who didn't hear that, I might have a diagram for you. Yes, we do have a diagram. Okay, so for example, like consider the athlete group ABC, right? If we were just doing like permutations, we could have been choosing ABC or like ACB or BAC or like, you know, as a matter of fact, there's 6 ways to choose A, B, and C, and 6 ways to choose A, B, and D, and you know, 6 ways to choose A, C, and D. So number of ways you can order each of these, right? Very, very foundational concept. You're dividing by the number of times you're only counting. So very, very important. If you don't forget this, it'll come up for the rest of your life. Okay. Let's come to the top question. How many ways can the 3 be chosen from 10 people and then assign the roles of captain, vice captain, and treasurer? Okay, I'll give you guys enough time to ponder this. Perhaps to proceed. So, this was this problem. Could have just started like a permutation, right? You could have just been like, 10 person could have been captain, and 9 could have been vice, and 8 could have been treasurer. Or you could have like chosen the 3 people, assigned the 3 roles, and typed it together. And in this step, you're basically undoing the division step in a combination, right? You're timesing it by 6 after you just divided it by 6. You got one or 2 more slides. So, do you have any questions about permutation comps? Yes? Well, the order of the rows does indeed matter, right? You could give if you like see it yeah, I think generally like if you have A, B, and C, like it matters that A is specifically captain, compared to A being vice captain. Oh, yeah, makes sense. Yeah, okay. All right. Next up is another type of combination called a stars and bars combination. So the definition says the number of ways to distribute n identical objects into k distinctive bins, allowing for an empty bin is n plus k minus 1 choose k minus 1. So this is a pretty typical question. So we have an example here. How many solutions does x1 plus x2 plus x3 equals to 5 have in non-negative integers? So x1, x2, and x3 are chosen from 0 to 5 inclusive. Like, don't worry, it doesn't make sense because like we learn through examples. Listen. Not bad, yeah, you can probably use this one. That's good. Other plugins, yes. Yes. Let's be rational.
So you have 3 bins, but you have 4 separators, and then two separators, and then you order the boxes and the separators, and then apply some of that.
That's pretty good. Yeah, you indeed are. What he just said is the correct, intuition to have behind this problem, which should be illustrated in an image here, right? So, so x1, x2, and x3 when there's no indicators. So we can represent the solution as 5 stars, basically the number, like each star represents one value of 1, and 2 bars, there's 2 of these dividers. And if we choose how we separate the stars using these bars, basically how we order those 5 stars and 2 dividers, each one we give some sort of unique situation, right? So the one we have here, we have 2, a bar, 1, bar, and 2. We have 2, 1, 2. And in that case, we just have 7 positions and we're choosing 2. So 7 choose 2 would be, why should be 21? Do we have any questions here? Right, because so the 5 is like each of these stars represents 1, right? There's 1, the value of 1. So what we introduce, which are formed from like amalgamations of the number 1. So we're considering each of these stars with a value of 1. Does that make sense? Okay, yeah. And yeah, adding 2 because like there are originally 3 numbers. But to have 3 numbers, you only need 2 dividers, right? Because you have 2 dividers and you have 3 groups. Because if you were to have 3 dividers, maybe you have like a third divider there, but that separates it into 4 groups, and you have just 3 numbers. You have 4 numbers. Which is why we have specifically, 2 dividers. Yeah. Okay. It's kind of weird because the diagram go backwards. We have another example here, which is how many ways can 10 identical chocolates be distributed among 4 children if each child gets at least 1? So it's kind of like a normal, starting bar problem, but it's different in the sense that you can't have like an empty basket. You can't give a child no chocolates. That'd be rather sad. So how do we approach this problem? I'll give everyone a bit of time to problem this issue. Right, does anyone have any ideas? Use the formula, but what numbers are you subbing to the formula? Yes, indeed, at case. Well, the interesting thing with using n equals to 10 in case 4 is that is the original situation where you have an empty basket, but we don't want to keep around no chocolates, right? So we're going to change these numbers in some way. What do you mean? Oh yeah, that is indeed another way you can do it. So what he's suggesting that you can have just the dividers between the chocolates, and if you just choose the dividers like specifically in the spots, and you don't have like 2 dividers in the same spot, you won't force a child to have no chocolates. That is another way to do it, sure. I on the previous slide, diagram I'm going to show it. So one simple way we could have slightly changed the numbers is that we just give every kid 1 chocolate, right? We just give that's 1, Ben 1, Cara 1, and Dan 1. If we give everyone a chocolate, then any way we want, like over here, we've given Cara 0 for the additional 6, but that doesn't really matter because we've already given her 1 there. So now we basically just do stars and bars, but instead of considering the original 10 chocolates, we can now just do 6, and now we pick up 3 dividers and 6 again. So that's another way of doing it. And like these words here said, and if you apply the formula, you have what? 6 plus 3 is 9, and then 9 choose 3. And if you do what they said, then 9 gaps within the 10 chocolates, and again, you're choosing 3 of these gaps. So that also works. Yeah, that's what we had before, and we're now up to the next section of the talk.
Thanks, David, for that. That was a very nice introduction to combinatorics and hopefully a revision of what some of us learned in high school. So now, ongoing from that part is something more theoretical and something that delves more deeper into, the symmetry of how we choose certain things under equivalence. So if we motivate with this example, so how many ways are there to arrange 3 people on a circular table? And 2 arrangements are identical if one can be obtained from the other by rotation. So this example here will be used to motivate a few definitions that we'll go over. So right off from the bat, if we were to think about this in the decision tree format of thinking, we have our so we have our initial node decisions that we made. Then we decide either red, blue, or green to go. Then we decide another person to sit down. And then at the end, we decide the last person to sit down. And we have a list of a bunch of configurations of all the allowable, of all the possible ways this can happen. So this set of configurations obviously does not account for this condition over here, that, 2 arrangements are identical if one can be obtained for the other rotation. So if you can rotate this configuration, if we rotate it maybe clockwise once, then we will arrive at green, red, blue. So we will arrive at this one over here. So technically, these 2 here are considered the same. So this is so we'll expand on this notion of the same in this slide over here, where we talk about equivalence relations. So an equivalence relation essentially is, it's an operator that defines what it means for 2 things to be. So a more formal way of saying this is that it's basically a binary operator such that the expression of 2 elements evaluates the true if x1 should be considered equivalent to x2 in the context of the counting problem. So when we define, we define when 2 configurations should be considered the same. So in the context of this problem, we have so another definition is this concept of an equivalence class. So the equivalence class for any element x, or in our case, any configuration, are the set of all the other configurations that are the same as that. So in this example, we have this configuration here that you can get where you have blue, red, and green sitting in this fashion. That's the same as this configuration here, which is the same as this configuration. That is because this can be rotated into this, which can be rotated into this. Similarly, you have another class of configurations where this can be rotated into this, which can be rotated into this. And so therefore, we've managed to partition or split up the total number of, to split up all the configurations into 2 sets. So based on what you see right now, could someone tell me what the answer is then for the above example? I'll just go back to this. So could someone tell me what the answer would be to this? Yeah, 2 exactly, because there's two classes over here that that you can partition the entire set of configurations into. Yeah, perfect. So another definition basically is known as the quotient set. So we see, so this symbol over here we'll refer to as this is our equivalence relation. This is basically how we're defining equality in the context of this problem. So this notation here just means the sets of all equivalence classes under this equivalence. So you got 2 of these sets within this massive set. So that's just how we define things. That's just some notation to keep in mind for the upcoming definitions, the upcoming theorems. So now let's expand this notion of equality by considering group actions. So a group action essentially is, it's basically an action on a configuration, which is a sort of movement or symmetry, and it maps one configuration to another configuration. So we can denote all the possible actions that we can take. We get G1, G2, G3 that rotate a configuration clockwise this amount. So could someone tell me what G3 here does? Yeah, Eamon, you had your hand up.
G3 is a 2-point re-rotation, or consider like a 1 pointing between that clockwise. Yeah, perfect, exactly. So it corresponds to this over here, this action over here.
So over here we have a diagram that shows all the possible group actions we could perform on this single configuration. So one group action is the action of do nothing. The other group action is we rotate 120. The other one is rotated 240. Yep. Now notice we can combine groups. So the combination of G2 and then G3 of 120 and 240 can be combined. And it comes out to just doing nothing because it rotates at 360 degrees. So you have this sort of arithmetic here where G2 plus G3 is essentially doing the same thing as G1. Yeah.
So how would like in set notation, how would this look?
So in set notation, it would look like so you basically have a set of all configurations, and this set of groups, these actions act on that set, is what we say. So the set that we're dealing with here is the set that's being dealt with here is just this over here. Like if you were to put a comma over here and wrap it with curly braces, that would literally be our configuration set that the actions are acting on. So if that answers the question. Yeah, perfect. So now, formalizing this arithmetic of group actions, we have the following rules, or you can call them observations. So for any set of group actions, it's defined to be a group action if and only if the set has to have the do nothing action. Composing any two actions produces another action in the set, and for every action there exists the action that undoes it. So back over here, G3, the opposite of G3 would be G2, because that would come back to the original configuration over here. So yeah, and another condition is that composing actions must be associative. So from before, if we apply G3 then G1 and then do G2, that's the same thing as doing G2 then G3 then applying G1. So that's just a few definitions that we have to keep in mind for considering what a valid group action is. Now, another definition here is this notion of a fix. So the fix of a group action basically is just the set of all configurations that do not change when that group action is applied. So over here, so for a set of group actions acting on S, a fix of an action is a set of all elements in that configuration set that remain unchanged after that group action is applied. So in our example, the only action that leaves a configuration unchanged is the do nothing action. So if we go back here, the do nothing action doesn't change a configuration, does it? Right? It just leaves it the same. So how can someone tell me how many elements would be in the fix of G1? Anyone have answers? So actually, it would just be the number of configurations that are already there. Because remember, note down the question. So we're trying to figure out how many configurations do not change, right, under the action of do not change. So that's going to be every configuration that exists. So it's just going to be 6, because that's how many configurations we calculated at the very beginning. So let's move on to the next slide. Yeah. So now this in general is generalizing basically what we're looking at in this question is a general counting problem involves determining the size of that quotient set that we determined earlier to be 2. And there's some specific equivalence that groups all configurations together that we have to apply to find that number of equivalence classes. So back to this example. Now, using all those definitions, we can see that our set of items that actions happen our set of items that actions happen are all configurations that we listed in our tree. So there are 6 of these for the do nothing action. And the idea of equivalence, under the idea of equivalence, there are group actions G1, G2, and G3. And each group's fix is the empty set except for the fix of the do nothing action. Yeah. Yeah, 3 minus 1 factorial from the, yeah. Oh, yeah. Yeah, that's the typo. Yeah, so that's only 3 minus 1 factorial. Yeah. Yeah, so then, yeah, so that gets us to 2 factorial in total, which is just 2. Yeah. So this leads to a bigger formula that we can look at. And it lets us calculate the number of unique configurations in a massive configuration set. And it's called Bernstein's limit. So the number of objects modular equivalents, right, is defined to be the average fix of each group action. So if you look at the earlier example, the fix of G2 of the rotate 120 degrees and the fix of 240 degrees rotation are 0, because if you rotate a configuration by 120 degrees, you aren't going to get that configuration back, are you? Right? It's not going to stay the same. Same with the 240. But then when you apply the do nothing action, all the configurations are what they are. They come back to themselves. So it's going to be 6 for the fix of G1 and then 0 for the rest. And now this magnitude of G just refers to the size of the action set. So what all possible actions you can be taking. So this here evaluates to take a good note of this formula, because we'll be doing a few examples and a few questions regarding this. So let's move on to this next example. So this next example is quite interesting actually, because it's very it's not very straightforward how you would approach this without knowing Bernstein from. So the bracelet problem. So how many bracelets can be made using 3 white and 3 black beads? Now, for this example, it's important to know when you wear a bracelet, it doesn't matter whether you reflect it and put it on your hand, or whether you just put it on your hand without doing anything. So you can reflect it and you can rotate a bracelet. So keep that in mind with the possible symmetries to keep note of. So I'll let you guys have a go at this for about maybe 2 minutes, 2-3 minutes, and then we'll go over how, we'll go over the solution for this. Let me know if you guys want me to go to the previous slide so you can note down both sides as a formula. Okay, I think that should be enough time. Now, yeah, it's not 5. Yeah, just to start off, can someone tell me what are all the possible symmetries that are at play over here? Remember before we had G1, G2, G3, which was rotating by 0 degrees, rotating by 120, rotating by 240. Yeah, what's the possible action set that we're dealing with? Mm-hmm. Yeah. That's so there's all 6 angles, so all 6 ways of rotating, right? That's one sort of action set. Like those are some elements of the action set. And you mentioned reflection. How many reflections are there going to be for this? How many ways can you reflect this? So yeah, 6 is right. So who said 6? Yeah, 6 is right. So you can reflect this 6 ways. So over here, this partial here. So these are all the 6 reflections that you can take. So you have your regular diagonal reflections that, you know, go across 2 points. And then you have your edge-based reflections that reflect across the edges of the hexagon. So now, yeah, and then of course you have your rotations as well. Going back. It's so weird. Yeah, so now let's look at our configuration set pretty much. What is the set that we're trying to find equivalence classes in? Now, the way we can sort of get a possible set for this is if you were to consider the number of ways you can arrange these 6 beads in a straight line, so without thinking about, you know, reflection, rotation, or even just the general shape of the hexagon, how many ways would you be able to do this? Well, it comes down to being able to arrange 3 black points, 3 white points in a straight line, which happens to be 6 choose 3 if you were to apply this as an advanced concept from earlier, or just apply just general combinations. Yeah, there's multiple ways you can do it. Yeah, that's how you get 20 possible configurations in this instance. So those obviously do not account for rotation, nor did it account for the reflections that you can take. So yeah, so just as a fun fact, the number of the symmetries that you can perform on a hexagon like this is referred to as the dihedral group on 6 vertices, and it's denoted by d6, which is a size of 12 because you can have 6 reflections and 6 rotations. So yeah, so now we'll look at the solution for this very simple problem. So now we're trying to find out all the fixes for each group action, because that's what Burnside's lemma demands. Now, if we look at the action of rotating once clockwise and rotating once anti-clockwise, so G60 and G300 degrees, how many of those configurations do you guys think are gonna, you know, have like no change? Do you think it's possible to not change a configuration if you rotate it once? No, right? It's practically, it doesn't make sense, right? Because you have 3 black and 3 white. If you rotate any configuration once, counterclockwise or clockwise, then it's going to obviously be a different configuration. So now the next instance, so therefore the fix that comes from G60 and G300 is going to be 0. So there's 0 such configurations that are unchanged with 360, sorry, with 60 and 360. Now the next one is, of course, when you rotate by 2 positions. When you rotate the hexagon, when you rotate it 120 degrees or 240. Yeah, so in this, you're rotating by 2, right? How many configurations do you think are going to be unchanged when you rotate by 2? It says 2 on the board, but why is that? Why is it 2? Does anyone have an explanation? What configurations, namely, are there? Okay, I'll give you guys a hint. Like, think about alternating, like alternating colors. I mean, it's just yeah, it's just alternating colors. Yeah, I think gave it a, yeah. So any configuration that has a black white, you know, configuration is going to be unchanged when you rotate it twice, right? Because you get back to it. Yeah. So there's 2 such ways of doing that, because you can start at the first point to be white or the second point to be white and alternate, and that's pretty much the set of all possible configurations. Now the third scenario here is going to be G of 180, where you rotate the entire thing 180 degrees. So this is not possible because there's 3 black and 3 white beads, and you need to force an even number of it needs to exist an even number of each color for that to happen, because of the parity that's on the board. So, and then finally, the last action over here is the do nothing action. And the do nothing action always leaves every configuration unchanged because it does nothing by definition. So, because there were 20 items in the configuration set before, the fix of the do nothing action is going to be 20 as well. So, putting all this information into Burnside's lemma. we also have to cover the reflection fixes. Yeah. So for each reflection, okay, so for each diagonal reflection, so that was across over here. How many of these, so what is the fix going to be for any one of them? Because the fix for any one of them is going to be the same for each reflection in the diagonal because it's symmetric arguments. So over here, the reflection of each one, you can pretty much choose this point get to be black and this point get to be white. So you have two ways of choosing your bipolar colors, and then for the number of ways you can choose these two, there's also two ways you can do that. And whatever's happening on this side has happened on this side. For that to be unchanged, for this reflection to be unchanged. And so therefore you get a total of 2 times 2 ways, and that's going to be 4. So for each diagonal reflection, there's going to be a fix of 4 contributing to it. So in total, the sum of all the fixes for each diagonal is going to be 12, because there's 3 such diagonal fixes. So diagonal reflections. Now, for the edge reflections, could someone explain to me why there are going to be 0 configurations for each edge reflection? Yeah.
On the board, for the edge reflections, it's like 3 on each side, and you have 3 blacks and 3 whites. For these 3, you can't you're gonna have the same number of. It's not possible with 3 blacks and 3 whites. You can't typically get like black, black, white, black, black. You're gonna have more blacks and more whites.
Yeah. Exactly. Yeah. So you could put a similar parity argument over here. Since there's an odd number of blacks and whites beads, that means you're gonna have, you won't be able to find any side of fixed. So yeah, that's right. So putting all this information into Bird's science lemma, the total number of actions that we have are 12, and the fixes of each action are shown up on the numerator, where this is the identity rotation. Also, this is the identity where you do nothing. This over here is going to be 2 from this is going to be 2 and 2 from the rotation of 240 and 120, and then these are going to be the fixes that contribute from the reflections of your diagrams. So in total, this comes out to 36 on 12. So therefore, there are 3 distinct bracelets: up to rotation, to reflection, and repetition of 8 colors. So that's the answer, pretty much. Now, yeah, your turn, guys. So I'll give you about maybe how much time do we have? Huh? You're probably 5 minutes. Okay, yeah. So take 5 minutes to answer any one of these questions. I'm only going to go over one of them because of time constraints. So yeah, you guys can choose which one you want to do, and I think the answer to 2 is going to be explained. So have about 5 minutes to have a go at these. Alright, guys, I think that should be time. Now, who'd rather go at question like any of these questions and got an answer? Anyone get an answer? Alright, that's okay. That's fine. We'll go for question 2. So, for those who are close to or on the road to get an answer, this is what the solution looks like for 1, 2, and 3. So, yeah. So, yeah. For the expression, there's 3 possible. Well, there's 4 possible symmetries involved. We rotate the board once, twice, or 3 times. So, yeah. Okay. So we'll go over the answer for number 2. So, how many ways are there to color the 4 corners of a square using 3 colors if 2 colorings are considered the same whenever one is a rotation of the other? So, since rotations are treated identical, we will use Burnside's lemma as usual, where our action group is going to consist of the do nothing action, rotate by 90, rotate by 180, or rotate by 270. So, these are the possible rotations that you can have. So, now, what's our so we count how many colorings are unchanged by each rotation. So for that, we need to know the total number of colorings that exist. So how many colorings exist in what are all the colorings that you can have without the symmetry? Can someone tell me? Yeah, 3 to 4. Yeah, good. So it's gonna be 81 because it was outside. So we have 3 to the 4 as our total number of configurations that you can get without the symmetry. So now let's look at the symmetry fixes. So for the 0-degree rotation with the do nothing rotation, of course every configuration is going to be unchanged. So we'll have this, the fix of that be 81. Now for the rotation of 90, the only way you can have a fix is if all corners are the same, all 4 corners are the same color. And of that, there are 3 because there's that many colorings. Oh, sorry, 2. Why is it the same? Okay, yeah. So then, yeah. Now with 180, when you rotate 180 degrees, opposite corners must match, and for that, there's going to be 3 squared, which is 9 such configurations. And then with the 270-degree rotation, all corners must be the same color with 790-degree rotation, which is going to be 3. So 3 possible configurations that are unchanged with this. So putting that to Burnside's formula, we take the average fix, and so that leaves us with 24. So yeah, the takeaway from Burnside's lemma is it just counts the symmetry classes by averaging the number of colorings fixed in each symmetry. Alrighty, now we're going to move on to our next part. So this is going to be inclusion and exclusion principle. I'm sure quite a number of us have looked over this in high school. But we'll be covering a few questions and examples related to this, as it forms quite an important part of what we'll look at in derangements. So the principle of inclusion and exclusion is used mainly when there's a direct overcount when you try to find the union of a bunch of sets. So you subtract off the amount you overcounted, but then if you over subtract how much you overcounted, then you have to add back the amount. So that's reflected here in you find the sum of all the individual individual sets, and then you subtract the section, and then you add back all three of the amount that you over subtracted. So this is the three set case. Of course, you can generalize this to n sets, but I believe for our examples we'll be having just this three set case. So this is the donut distribution problem. A baker has 6 identical glazed donuts to give to 3 kids: Alex, Blake, and Charlie. Now, there are constraints to this question because their parents don't let them have a certain number of donuts. So Alex can only receive at most 1 because he can't have a lot of donuts. And Blake can receive at most 2, and Charlie can receive at most 3, right? So how many ways are there to distribute these donuts? Can someone have like a go at this? Actually, I'll give you guys like 1 or 2 minutes to reason it out. And then I'll ask. Yep. Yes. Okay, all right, guys. So, intuitively thinking about it, what's the only way this can happen? Like, what's the most obvious example that jumps out to you as the most obvious distribution? Yeah. They all get their maximum limits. Exactly, they all get their maximum limits. So there's one way of distributing this. So it's going to be 1, 2, and 3. So that's quite simple because you can intuitively think about it like this. But if we were to take the more structured approach, let's say the question had instead of 6 there was like 8 or something. Or, yeah, if there were not 3 kids, but 4 or 5. So we would approach it in this manner. So the parent constraints are A must be less than or equal to 1, B must be less than or equal to 2, and C must be less than or equal to 3, where A, B, and C are the number of donuts Alex, Blake, and Charlie receive. So effectively, we're trying to solve the problem where we're trying to designate 6 donuts into 3 consumers. So 6 stars and, sorry, there's a number of items and then there's a number of bits. So it's similar to the stars and bars problem. So, and such that with the additional constraint where A is less than 1, B is less than 2, and C is less than or equal to 3. Yeah. And they're all greater than 0. Now, let's count the number of ways of doing this without these constraints. So the number of unrestricted distributions is just the basic stars and bars example that we had earlier, where we have n is 6 and k is 3. So then we'll have 28 overall distributions if none of them had any sugar limits and their parents were all, and they didn't care. So now what we're going to do is we're going to define the bad sense. Like what is, what has to happen? What shouldn't happen? So over here, the event where Alex gets at least 2 versus Blake gets at least 3 versus Charlie gets at least 4. So so we define these as sets. Therefore, by the total carrying result, we have to subtract away by what we don't want. So we'll have the total number of configurations 28, and we want to subtract by the event that A or B or C happens. So that's because we don't want them to happen. And so effectively, our problem is reduced to finding the size of the union of A, B, and C. So let's move to that. Now, we count the single violations because we're trying to find, because by inclusion exclusion over here, we have the single violations over here, the double violations over here, and the triple violations over here. So the number of single violations. So let's see this. So the size of A. So give Alex 2 donuts first. So we have the restriction that A must be greater than or equal to 2. So if we set A to be greater than or equal to 2, then the number on the right-hand side has to be 4 because we've already given 2 to Alex. And so it effectively reduces down to this stars and bars question where the sum of A prime, B, and C has to equal 4. And we can use starting bars and get 15 for that. Now, similarly for Blake violating B greater than or equal to 3, we'll have we have this question where you subtract 3 from 6 on the right hand side. 0 to A plus B prime plus equals 3. Number of solutions for that is 10. And then, yeah. And then for C, it's the same, it's a similar thing, except you subtract 4 from 6, from 4 from the total when you go through this problem. So you're going to have 6 in total using stars and bars. So the number of single violations is going to be, is naively thinking about it without, thinking about any overcounting. You could say it's 15 plus 10 plus 6, but that's too much. We've double counted. So we're going to have to reduce by the double violations. So now we count the intersections. So over here, where Alex and Blake both violate, so A and B happening, that means that you pre-assign 5 donuts to go to A and pre-assign 2 donuts to go to A, pre-assign 3 donuts to go to B. That leaves the problem to be A plus, that leaves the residual problem to be this, where you have A prime, B prime plus C equal 1, because 6 plus 5 is 1. And so the number of solutions for that using stars and bars would just be 3. Now, Alex and Charlie both violate. You have a similar sort of process for that. So yeah, so that's going to be, so you pre-assign 2 plus 4, so you pre-assign 6 donuts, then that's going to be A dash B plus C equals 0, of which there's only one way of that happening. And then, and then for B and C violating, that would require, that's over here 0. And all 3 violate, okay? So that's the last instance that we want, because we have overcounted our subtractions, overcounted the double violations. So that means A must be greater than 2, B must be greater than 3, and C must be greater than 4. So that would require at least 2 plus 3 plus 4 equals 9 with donuts, which is impossible because you only have 6 donuts over here. So the intersection of all those 3 events is going to be 0. So then plugging that into the inclusion-exclusion formula, we see that the union of A, B, and C of the wrong sets of what they can't do is going to be 27. Therefore, the number of valid distributions is just going to be 28 minus 27, which is just 1. And that one distribution from before is just going to be where each person gets their limit. So 1, 2, and 3. We'll have 2, so we'll have 1 as a final answer. All right, cool. So that was pretty much basic principle of inclusion and exclusion. Now we're going to look at a specific subset of problems known as derangements. So a derangement is basically a permutation in which no element appears in its original position. So nothing can map to where it was originally. So it has no fixes, right, from before. If we remember our definition of what a fix is, it has no fixes because no element maps to itself, maps to this position. So we can see over here, a regular arrangement would just have this, could be this. But a derangement means A1 can't go to A1's original, A2 can't go to A3's original, so on and so forth till AN. They all have to be in different places. Okay, so so this is just a recap of what we just said. Now, let's look at a derangement problem. An administrator writes n personalized letters and prepares n matching envelopes. This is a very typical envelope question that many of you may have seen in Greenbook or other places. So the question is, how many ways can the administrator stuff the letters so that no employee receives their own letter, right? Like this administrator's in a rush and they've just chucked it into whatever envelope. How many ways, what's the worst possible scenario when no one gets the letter that they were designated to? How many ways are there for doing such a thing? Can you guys think about it maybe for a minute, and then we'll go over and answer. Okay, so any ideas? Yeah.
least one. Most of the case was one of the states. So
Yeah, pretty much. Yeah. So we find the normal entire possibilities of arranging things and we subtract away the complementary things, as we did in the previous example. So in this case, so over here, the number of ways to assign n letters to n envelopes is going to be n factorial. Because it's the number of permutations. You consider it as arranging n distinct items in a line. It's the same thing. So this counts all the permutations without, or including ones with and without fixed points. But our goal is to remove all permutations with at least one fixed point. So then we're left with the ones that do not have any fixed points, which are the derangements. So over here, let's define the event AI to be the letter. So the letter I is placed in the event that letter I is placed in the correct envelope. So then effectively we want to count the permutations outside A1 or A2 or so on and so forth to AN. So the number of derangements totally is going to be the total number minus the complement case over here. So where each AI is correct, right? So but we don't. Okay. So coming back over here, suppose exactly one letter is fixed, right? So the case where one letter is fixed in its right place. So then we commute the remaining n minus 1 letters freely, however they want to go. So that leaves us with n minus 1 factorial arrangements of doing such a thing. Now, there are n such sets, so therefore we multiply by n because you can have the first one be fixed, the second one be fixed, the third one, so on and so forth, which is why we multiply that by the number of letters. So there's going to be n times n minus 1 factorial. Now, the next case is going to be, let's say, if k specific letters are fixed, right, then the remaining n minus k letters must be permuted amongst. So that leaves us with n minus k factorial. And then how many ways can you have, how many ways can you choose k specific letters from n? Well, we did this at the very beginning, didn't we? It's just going to be n choose k. So n choose k times n minus k factorial is going to be the total contribution from each one of these. So using our inclusion and exclusion principle, we see that the total number of derangements of n letters is just going to be n minus the sum of all these guys over here, each k, adjusted by a plus and a minus each time. So that simplifies down to this formula over here. Now, those who have done something, those who know the Taylor expansion of e to the x would kind of recognize this formula because you see a k factorial over here and you see a minus 1 over k over here. So that will cause you, so then you kind of think about it. And notice that for large n factorial converges to, dn converges to n factorial of e. Because this over here is going to be e to the negative 1. So this is, e to the negative x, and then that's going to be e to the power of 1 over the denominator. Yeah. So if you want to solve this question really quickly, actually, there's a bit of additional information for this. If you want to find this question really quickly, you just plug in n over here and then find the nearest integer for it, because that'll give you the exact solution. So if you know, like let's say you've been asked this in an interview, like literally just say that, oh, if there are like three envelopes and 3 letters, it's going to be 3 factorial divided by e, and you find the nearest integer to that. So yeah, that's just a quick way of doing it from the inclusion and exclusion. So let's look at the next case. So let's look at the next example. So in this example, we have a teacher has graded the tests of n students and wants to hand it back. How many different ways can the teacher return the tests such that exactly k students receive their own correct test and the remaining n minus k receive someone else's test? So it's kind of like a subset of, well, no, yeah, it's kind of like a subset of, like a subtype of the original problem over here, where we fix the first k students. But then, how many ways would there be to fix k students out of n students? Can someone tell me? How many ways can you choose k students out of n? N choose k, right? Yeah. N choose k, it's very basic, right? So, yeah, it's going to be n choose k. So this example over here is just an arrangement where you have the student 1 getting his own mark back and the student 3 getting their own mark back. And that is an acceptable configuration because k over here is true in this instance. Okay, so Yeah, so we choose our fixed points. We want exactly case students to get their own test back. So we first choose what the case students are. That's going to be entries K, as we established before. And then once these case students are chosen, their tests are fixed in place. So effectively, we're looking at the derangements of all the remaining students. So from the previous formula, how many derangements are there of all the remaining students? Yeah, pretty much. Yeah. Well, the nearest integer for that. Yeah. So yeah, you pretty much you find d of n minus k. So that's going to be that's going to evaluate to so there are n minus k ways of such. Okay, so the total number of ways is going to be n choose k times d of n minus k. You first choose those k students and then you derange all the remaining students, which sounds really simple. Like, okay, yeah. All right, now you guys have got these questions. So these are a few brain teaser questions that we asked in the interview. Yeah. I think we have a solution for number 2 over here. Next slide. So 5 minutes for this, guys, and then we'll move on. Okay, guys, that should be it pretty much for the amount of time you guys have to work on this. So here you are. Here are the answers for those past 4 questions. Did anyone get these? Okay, well, these slides, hopefully they're going to be made public, and you guys can like have a proper. So yeah, okay. So let's explain the second question over here, where a deck contains 50 cards. How many 5-card hands contain at least 1 card from each suit? So basically, we want to count all the hands and then subtract the hands that miss at least 1 suit from the previous instance before. So it's just it's another case of subtracting away the complement. So over here we have let AI be the set of 5-card hands that are missing a suit S. So A clubs is going to be AS be the set of 5-card hands. So A clubs is going to be missing club suit in their hand. So we want hands that miss those suits. So the way we're going to do that is we're going to find the total number of ways of getting the 5 cards in your hand, and subtracting away the event where these where a club is missing, or diamond is missing, or card is missing, or spade is missing. So by inclusion and exclusion principle, you get the number of valid configurations to be this over here, where you have 4 choose 1 times 39 choose 5, so on and so forth. And calculating that, you probably a calculator or is good at mental math to give you that result. and so that's going to be 68,500. Sorry, 685,464. Okay, right. So I guess now we'll have a bit of a break.
Yeah.
Before we start.
Hey guys, thank you so much for listening so far. We're almost done with today's lecture, but we just want to give you guys a quick 2-minute break. There will be pizza coming at the end of this, so you guys can have some free food. So yeah, just we're going to take a 2-minute break, and then we're going to finish off with objectives.
Wait, what the? Wait, they just cancelled our order. Wait, do I just reorder now?
Yeah, can you? They should be getting it.
I'm gonna cancel. I've never had it. Yeah.
They should get it. It's okay. Like people may have to wait. Keep it at the top. Sorry.
How many? No, it's okay. Wait, do I have money? I just used some of my phone.
Alright guys, I hope that's enough of a break for now. So we'll start the last part of this workshop with bijections. So a bijection essentially refers to a one-to-one mapping between two sets. Earlier, Eamon talked about what a function is essentially, and it's a mapping between two sets. But a bijection is a special type of function that maps one element to another element in that set, between two sets. So over here, the way we implement bijections as a method to solve combinatorics questions is we start with a set that's difficult to count. And then we find a one-to-one correspondence with that set and another set. And that other set is a bit easier to count, and we count the easier set. So that's the general framework of bijection questions. Now, yeah, so over here we have a path counting example. So how many paths are there from 0 to n in a grid, moving only right or up that stay below the diagonal line? Now, the way we're going to approach this question is we first encode what it means to have a valid path. Now, a valid path is encoded by a sequence of moves, which is either right or up, R or U. And any valid path that goes from 0, 0 to n must have n copies of R and n copies of U, because n copies of R and n copies of U. So therefore, every unrestricted path corresponds to a sequence of length 2n with n right moves and n up moves. So the number of ways you can arrange n right moves and n up moves is going to be 2n choose n, because that's the number of combinations of n. So now we apply the constraint, because that counts all the possible types of paths that we have. Now, applying the constraint over here, we want to stay below the diagonal. So every prefix of the sequence must satisfy the number of up moves being less than the number of right moves. Because if that isn't satisfied, then it means that we've crossed the diagonal, conceptually speaking. So this is known as a Dyke path. And it's basically a path from 0, 0 to n using RU that every prefix, well, at every prefix you have the number of up moves being less than the number of right moves. So our problem is asking for the number of Dyke paths of length 2n. Now we count the valid parts by subtracting the invalid parts from all the parts that exist. We know all the parts is 2n choose n from before, and so it remains to count the parts where at some point u is greater than r. So these are exactly the parts that cross above that diagonal. So we want to count the violations of that condition. So that's what we're reducing the problem to. Yeah. Okay, so now the way we're going to map this counting problem is we count all the invalid paths from n, and we claim that it's in bijection with the paths from 0, 0 to n minus 1, n plus 1. So we take an invalid path and find the first time it goes above the diagonal, and then at that very instance, the path is moved to a point where the number of up is equal to the number of right plus 1, because it's above that diagonal line from before. And so that changes the total number of moves from n lots of r plus n lots of u to n minus 1 lots of r plus n plus 1 lots of u. And so note that still the number of number of elements is unchanged as n in that as 2n in that sequence. So the reflected path ends at this. So the size of those two sets that we've compared are the same. Now, so intuitively thinking about this, this is what a violation, like every path is violated after a point, after it intersects that line above the median line, because we are counting the complement case. So by the way, these slides are going to be up after the workshop, so if something doesn't make sense, we'll probably read through it and reason through it. Yeah. So now the reflection process is reversible, so that those sets mapping to each other is a bijection, and here is why. Therefore we find the number of violations to be 2n choose n minus n plus 1, and the number of valid paths is therefore going to be the total minus that violation. And if you use that combinatorial identity that we derived in the first part, you get this out to be 1 on n plus 1 times 2n choose n. And so this is actually a Catalan number. So it's called the nth Catalan number, and it's very specific to this example, and it's used quite heavily in a lot of quant interviews and a lot of other questions. So yeah, so this is our key takeaway. Yeah, we're finding valid paths that we subtracted from the total. Now, this is another question. I'll just go over the question. We won't go over the example very quickly. We won't go over the example in detail. But the question is, a trader makes exactly 4 buy trades and 4 sell trades during the day. And they start with an inventory at 0 and short selling is not allowed. So in how many different orders can those 8 trades occur if the inventory must never be negative? So you can't sell more than 5. So over here, just to iterate through this really quickly, it's pretty much the same thing as the regular Catalan numbers, except where you consider a buy to be moved right in one direction and consider a sell to be moved up, and you're trying to get, and you want to allow to sell, and it's for each point, each possible positive value. So yeah, so this is an example path. Pretty much. Now, yeah, so these are all the DAC paths with 4 right steps and 4 up steps, and that resolves to be 14 if you plug it into the Catalan number formula. Now, here's another question. It's very similar to the other question about the DAC paths, but in this case, we have an upper constraint, we have a lower constraint and upper constraint. So each trade changes inventory by 1 or -1. And we have a market maker that starts with 0, and it's given that he ends with 0 as well by the end of these 16 trades. And he must satisfy the risk limits where his inventory cannot be less than 0 or be greater than 3. How many possible inventory paths are there? Now, if you go really quickly through this, it's pretty much you have 4 states that this entire thing could be in. So it's not going to be the same as the Catalan number question, because it's actually a dynamic programming question in disguise, where you have 4 possible states and you have transitions between them. If you have a set of recurrence relations that you can derive, and each trade moves inventory to a neighboring state. And so you use this recurrence relation that you've derived over here to count up from 0 through to 16. And that leads to be 610 possible with that upper barrier of the inventory being less than 3. So yeah, this is a very similar thing is seen in Markov chains as well. If this is a probability function. So yeah, that's pretty much the end of this part. Yeah, that's the point of. You have the back is.
Oh, sweet. So to finish up, I'm gonna have a quick chat about recursion. So in counting is a really useful technique to try and count some things. So as it says in the border recursive description, we'll express the number of configurations of something of size n in terms of the number of configurations of smaller sizes. So these usually consist of a couple of things, like a recurrence relation, as shown. So say maybe an is some function of these smaller cases, and then some base cases. And these base cases are usually quite trivial, they'll work out. And then to solve these things, we can do one of 2 things. We can just back substitute, or you can also go into generating functions to find a closed form. But that's going to be beyond the scope of today's talk. So finally, this isn't really too theory heavy, but it can be challenging the first time you see it, so it's useful to work through a few examples. And my strategy to solve most of these problems is just to consider what can happen in the first or final step when you're constructing it. So we're going to start with an example. I think Eddie went through this example a bit before, but I want us to try and solve this in a recursive manner. So we're going to have a postman, and he's going to deliver n letters to n different addresses. And I want to know how many ways we can do this such that no letter is delivered to the correct address. So we can represent this as a permutation sigma, if you like that notation. And we want to know for how many ways can we satisfy this such that sigma of I does not equal I for all I. So perhaps I'm going to let you guys have a go at this, see if you can try and come up with some sort of recursive description, and perhaps let the n denote the number of such configurations of size n, and let's see if you can try and write this in terms of some d for some smaller n's, and then find some base cases. So I'll give you like a few minutes to have a go at that, then we'll go through the solution. Oh, sweet. So does anyone have any like ideas on how you could start to solve something like this? Or any intuition about the problem? Yeah, I would agree. Do you have any intuition about how we can develop some sort of relationship for Dn? Yeah. Yeah, that is actually very close. And the solution we're going for here, so I'm just going to consider letter 1, and this letter must be delivered to some address J. Obviously, J can't equal 1 because then it's just invalid. And there's going to be n minus 1 choices for J. And here's the two cases I'm going to split it into. The first case, if J is delivered to address 1, then this is actually going to reduce to a problem of n minus 2, because we're going to have letter J at address J and letter 1. Sorry, letter 1 at address J and letter J at address 1. So essentially we've got, like, if you like thinking graphically, we've got some sort of closed cycle here, and we're going to have a reduced problem on n minus 2. And the other case, which is what you were getting at, is letter J is just not delivered to address 1, and now we're just going to consider this is a problem of n minus 1 letters. So thus we can sort of arrive at this recursive relationship. And then the last thing we need, as we sort of said, is some base cases. So for here, obviously, if we've only got one letter and one address, it must be delivered to the correct place. That's an invalid case. So there's 0 ways to validly do this. And if we have 2 letters and 2 addresses, there's only one possible permutation, such that they're both different. So that was our first example. We're going to do another example of a recursion problem. This one may be a little bit more challenging, but we'll see how we go. So I'm going to have a... Yeah. Yeah, that's a really good question. One of these formulas, you can actually turn it into a formula in terms of n, and that would require what we call generating functions. We probably don't have time to go into generating functions today, but definitely a cool thing to look up if you're interested. But similarly, like, say if you got something like this in an interview and you ask for like D9, like you could pretty simply like just back substitute. Cool. So now we're going to move here to solving a tiling problem. I'm going to have a board of 2 by n, and we're going to tile this using dominoes and tromios. And those tromios are just think of an L-shaped tile. I've got some examples on the next slide. So if we go to that, here's some example tilings. So for t equals 1, there's just the one tiling, the one vertical domino. For t equals 2, we've got a few 2 different tilings. And for t equals 3, we've got 3 example tilings, but there's obviously a few more by commuting these. And yeah, so I'll get you guys to have a go at this and try and think of if you can find some sort of recursive relationship for these things. This one's a bit challenging, but just think of all the different like moves that you can do on the first turn on an empty board, and we'll go from there. So in the interest of time, maybe we'll start going through the solution. Did anyone have any baseline ideas of how we could go about this? Yeah? Yep, okay. Yep. Yeah, so that's a very good intuition. That's very close to the actual solution. So what we've got back here is, as let us just, for notation's sake, let us denote Tn entirely of a full 2 by n board. And then as you were saying, how we find this problem is if there's like one gap. Let's like denote this other auxiliary quantity and we'll call it Gn. So cool, so this is like what our times will look like. So Tn is just a full board. This is an example of n equals to 4. And then we also have GN, which is a full board but with one gap at the end. So now what we're going to do is we're going to try and find some recursive relationships in terms of these two things. So this is what we came up with. So as you were saying, we do get this Tn is equal to this Tn minus 1. You can think of that as placing a vertical domino, and Tn minus 2, which is the two horizontal dominoes. And then we get this other quantity, 2 times Gn minus 1. So you can think we get the 2, but there's obviously with the tronios, we can go with the gap at the bottom or the gap at the top. So there's 2 different ways. And now we need to think how we develop our recursive formula for Gn. And so what we can do is, actually, can anyone tell me, does anyone have any intuition of how we'll get this relationship down here? Yep. Yeah, so to get this one, what we're going to do is say this Gn minus 1. Imagine we've got like a imagine we've got a board here, and we've got the tiling that looks like this. To get this Gn minus 1, that's just going to come back from placing a domino like this. And now we've got another arrangement of Gn minus 1, and this Tn minus 2. Does anyone know how we're going to get that, or what we're going to do? Yeah. Yeah, exactly. That's it. So then we're going to get this recursive formula like this. In the interest of time, we'll probably move on. But yeah, you can also draw out your base cases and then just back substitute to get like a an answer for a tiling of a board that's 2 by n. That makes sense. Cool. We've got a few example problems about our workshop, I guess. In the interest of time, we'll probably only have time for one of them. So let's have a go at this one. So what this problem is I'm going to have 15 ones, and I'm randomly going to insert plus signs between any of these ones. And then finally, I'm going to evaluate the sum, and I want to know if this number is divisible by 30. So let you guys have a chat to the person next to you, see what you can come up with, and we'll go through it in a minute. Does anyone have like any ideas of where they'll start when solving this problem? Yep. Yeah, that's like pretty much exactly the solution. Could you like explain why you need 9 plus signs? Okay.
For divisible by 5, you need either 4 plus sign or 9 plus sign. 4 plus sign doesn't.
Yeah. Yeah, that's like pretty much that's completely valid. Can you like judge going from that? Could you like tell us how many ways there are to how many such expressions are divisible by 30? Yeah. Yeah, exactly. That's a really good explanation. To briefly go over that. So imagine this is like we're splitting this into a bunch of gaps between our ones, and then we're deciding whether to place a plus sign between them or not. So what I know is 30 is equal to 10 times 3. so I need such a number to be divisible by 10 and also divisible by 3. I'm going to remember from when I was in primary school that there was a trick that I learned, and if you add all the digits up and it's divisible by 3, that number is going to be divisible by 3. And then also, obviously, it has to be divisible by 10, which means such a number must end in a 0. So that's how I'm going to arrive at that. Okay, we need 9 plus signs, because that's the only valid number that can hold to get this divisible by 10. And then a quick check would show this is also divisible by 3. And then exactly like you pointed out, if we know we've got 9 plus signs and we've got 14 gaps, we can simply just use our combinations formula as we discussed earlier in the workshop to get our final answer. As like one little follow-up problem, could anyone tell me the if we do this, randomly pick if there's going to be a plus sign between the numbers or not, can anyone tell me the probability that this number is going to be divisible by 30? You can place as many as you want. But to make it valid, you can place 9. Make it divisible by 30. Yeah. Do you have it? Yeah, perfect. Yeah. Do you like have some intuition of how we got there for everyone else? Yeah, exactly. Yeah. So there's 2 to the 14 total ways, and we've just found a valid way, so we just divide it to get our probability. There's one more problem, but I believe it's 6 o'clock, and I think we have to be out of here. But if you're interested in the final problem, I think you can download these slides. They should be available, and you can have a go at that at home if you want. Thanks for coming.
Okay, guys, thank you so much for coming today. We will have pizza arriving in about 10 minutes, and then we'll be downstairs, so we can stay around for a few minutes and grab some food. And this was our first workshop of the week. We also have another workshop tomorrow. So that's on C++ and template programming. So if you are interested in getting into quant training as a dev, that will be a workshop with a collaboration with SINCS, which is the Sydney Uni Computing Society. So yeah, thank you so much.
Yeah.